Okay, let's get this second session started. So just to remind you about this parsing stage, parsing process, we've got 3 stages. So the first one was this tagging stage that I'm going to talk about in a moment. And we've got a part of speech tagging phase which we'll use as well as the super tagging. So remember, the super tagging is the tagging that assigns the CCG lexical categories to the words in the sentence. And I'll say a little bit about maximum entropy tagging, but not too much. And in fact, if you like, you can think of using an HMM tagger for this process. Probably won't do quite as well as the tagger I'm about to describe, but it's just a tagging problem, that's my point. And then the second stage, we'll use the combinatory rules I've talked about, the application, type raising, composition, and so on, to combine the categories together. We'll use a standard chart parsing algorithm for that. I'll talk a little bit about the CKY algorithm. And then using some model, today I'm going to talk about a perceptron, we'll find the highest scoring derivation, and the Viterbi algorithm does that efficiently. Let me just make a point. Someone asked me a really good question at the end of the last session, which is, when we're doing something like type raising, how do we decide when and where to do it? It's a good question. I always forget in my mind that, of course, a natural way to think about this process is that when you're doing the parsing, somehow you're making a decision as you go along whether to do this rule or that rule. And you certainly could build a parser like that. So what I mean by that is that you might have some statistical model that says, at this point in the process, do type raising, or at this point in the process, don't. And presumably, if we've got some sort of CCG parser in our head that Mark Steedman believes we have, then that sort of thing presumably is going off. But this parser doesn't work like that at all. So what happens is we always do type raising. So when I say combine the categories using the combinatory rules, we'll just combine everything. We'll do everything we possibly can, and only right at the end at stage 3 will we go back down and find the highest scoring derivation. So we're not ruling anything out. We're considering every possible analysis given the lexical categories that we assigned, and then finally at the end find the highest scoring derivation. So I'll just talk a little bit about this maximum entropy tagger that we've got. And first of all, I'll use pos tagging as an example that you've all seen before, context of HMM tagging. So here we've got, you can see some pos tags in blue, and here are the lexical categories, but I'll come on to the super tagging stage in a moment. So these are the basic grammatical categories you've got in the Penn tree bank, things like NMP's proper noun, VBD, past tense verb, CD, cardinal number, and so on. And there are 45 of those pos tags. So the pos tagging task is, given a sentence of English, in this case as input, assign one of these labels to each word. Now the way that you do that with a so-called maximum entropy tagger, this is possibly the most popular way of doing tagging, I would say, since Ratnaparky introduced it in '98. Again, another student of Joshi's, it turns out, at the University of Pennsylvania. The basic idea is very simple. We're going to use the probability of a tag given some local context, and I'll be precise about what I mean by context in a moment. And it takes this particular form, and I'll describe this form again in a moment as well. But the basic idea is very simple. As I said, if we want the probability of a whole tag sequence, given some word sequence, given some sentence, all we'll do is take the probabilities of each individual tag given its local context and just multiply them together. So for example, probability of this tag sequence, conditional probability will be the probability of this NMP tag given its context times the probability of this NMP tag given its context, and so on, all the way to the end of the sentence. Now we're going to use a machine learning approach here, and we're going to use features. So you've seen how features can be used for machine learning. In this case, the mathematical definition of a feature is basically a function of a tag and a particular context. So we'll see some examples of that in a bit later, but the basic idea here is that these feature functions are what are often called indicator functions. They're binary valued, so they take the value mathematically 0 or 1. So the idea is they're just picking out bits of the local context that might be useful for telling us what the correct tag should be. So let me try and give you some examples. So there might be some feature, for example, that tells us what the previous word is. That's going to be really useful. So let's take, say, this word here, share. Now, of course, that could be a verb as well. It's ambiguous. How do I know that it's a common noun? Well, the fact that the previous word is a is a really big clue. So we're going to have some feature in our model that's just some function, remember, of the context, that basically tells us what the previous word is. So there'll be some feature that says, if the previous word is a, and I'm considering the NN tag, then I take the value 1. If not, I take the value 0. So it's just picking out bits of the context. And we end up with millions of these features, because a lot of them are based on words, so they're highly productive. So you can see with this log linear form, it's called log linear because if I take the log of that, I end up with this linear sum. All that's happening is that these feature functions pick out, for a particular tag and a particular context, all the relevant bits of that context that we use for making the decision, namely all those that got the value 1. And for any particular tag and context, there'd probably be about 20 features that actually fired, in other words, had the value 1. Most of them would be 0, about 20 or 30 that had the value 1. And each one of those is associated with a weight, these lambda values here, and that's what we have to learn in the machine learning process. So the idea is that there will be some elements of the context and given a particular tag that will have a high value weight because they're indicative of a particular tag. So for example, if we go back to this one, in this case, when I have the feature, the tag that I'm considering is common noun and the previous word is a, I'd expect that to have a high weight because the previous word being a is a really strong indicator that we're looking at a common noun. Likewise, there will be a feature that says if the previous tag I've just assigned is dt, determiner, and I'm considering a common noun, then again that would be a feature, and again I would expect that to have a high weight, or those weights are learned automatically from the data. So you can see that for a particular tag and context, this will get a high probability if all the features that fire, that are on for this particular context, have high weights. Very intuitive. So if all the features that I'm looking at indicate that this is the correct tag for that context, then we get a high value. And this particular form is a very common exponential form. You see these sorts of models an awful lot in natural language processing. And we just have this normalization constant at the bottom. I've not defined it here, but it basically just means that we end up with a probability distribution. So when we add up all the probabilities for all the possible tags given a context, they sum to 1. And like I said, when we want to know the probability of a whole tag sequence given a sentence, we'll just take the product of all the probabilities. So I've not told you yet what the context is. We'll have a very simple definition. We'll just use the 5-word window surrounding the target word. By the target word, I mean the word that we're currently tagging. So I should have said this tagging process will go from left to right, like you've seen with the HMM tagger. And what features will we use? Oh yeah, so we're going to use the words in the window. Of course, we'll look at the word itself. That's going to be a really big, important clue as to what the correct tag would be. But we'll also look at 2 words either side. We'll look at the 2 previously assigned tags. But the nice thing about this maximum entropy tagging is the reason I'm telling you about it is because there's quite a lot of flexibility in terms of the features that we can define. So we can use suffix information. We can have a feature that says is the word capitalized and so on. So let me give you a few more examples. So if we're tagging, say, this word here, increased, we'll look at the 2 previous words, the 2 previous tags, because we've already assigned those going left to right. We'll look at the next 2 words, so it's and quarterly. But we can also be really flexible and say things like, there's a feature that says the last 2 letters in this word are ed, because that's going to be a strong clue that it's a past tense verb, a VBD. Now, of course, for a word like increased, you've probably seen it enough in your data that you know that it's probably a VBD anyway. But make up some verb in your head that's got a past tense form with an ed at the end. You've never seen it in your data, but the fact that it ends in ed is a really strong indicator that the tag is VBD. So a bit more on these features, how we define them. So these are defined with something called a contextual predicate. And again, a contextual predicate is just as I've described it, just picks out a bit of the local context that's useful for making the decision about the tag. So here's a nice example. We have a contextual predicate that says if the word that I'm tagging is the word that I'm trying to tag is the word the, and the tag I'm considering is determiner, then this takes the value 1, otherwise it's 0. So taking the value 1 just means this feature fires, it's just picking out a bit of that context, namely the word that we're actually tagging. And these are called contextual predicates. And as I said, the nice thing about this approach is that these features can be arbitrary properties of the context. We don't need the features to be independent. So when you looked at HMM tagging with that sort of generative model, you have to be, you have to make certain independence assumptions when you're multiplying the probabilities together. We don't have to do any of that here. It's very flexible. And for setting the weights, I'm not going to talk too much about this. There are a variety of training algorithms available. And in fact, one of the algorithms you can use is the perceptron algorithm that I'll talk about in the context of the parsing. But you could apply that to this log linear tagging model as well. So, okay, so that was just a very short introduction to maximum entropy tagging. As I said, if that went over your head, just think of this super tagging problem as basically tagging, and you can apply an HMM tagger to it if you like. So the reason I've chosen this example and got these words in blue is because I want to go back to this idea that CCG super tagging can be thought of as almost parsing. Remember I talked about this idea of almost parsing in the last session. So I've got two made up sentences here, and the reason these are in blue is because these are all categories that are assigned to prepositions. So in the Penn tree bank, the part of speech tag for each of those words would just be IN. That's the preposition tag in the Penn tree bank. But you can see here that each one of these has got a different category. And the reason is that in this example here, the word on is considered to be a complement of the word goes. So you can see here that the word goes has got this category where it's looking to the right for a PP. So in CCG bank, the way that prepositional phrase complements are represented is as a PP. So a complement is just a unit or a constituent that the verb needs to be complete. Remember, that's the idea with these categories. It needs this on the road in order to make a complete sentence. Whereas this one here is what's called an adjunct or a modifier. It's optional. We don't have to say he goes with his piano. It's optional information. You can see that we've got a different category here. So just to go through what this category means, we're looking first of all to the right for a noun phrase, which is his piano, and then it becomes something looking to the left for a sentence missing a noun phrase to the left. So all that's going to happen is we'll pick up his piano, the MP, and then that will eventually modify this S back MP over here. So my point is that in this example, once we've got this category correct, we know that with is going to modify the word goes and not modify road. So in fact here we've got a PP attachment example, like the eat the pizza with a fork. So there's an awful lot of information in these categories, and you can see why it's called almost parsing, because this sort of PP attachment problem is normally considered to be a parsing problem. And here, the reason I've chosen this example is because it's an adjunct again, so it's optional information. We don't have to say with global implications. But now it's attaching to the noun phrase, so we're looking for MP to the right, global implications, MP to the left, a bit of conflict. Yeah?
Does that mean when you're trying to decide the tag for ways you have to parse the process?
Oh, okay, great question, yeah. So almost parsing, it sounds like you have to do the parsing first almost to make the decision. Now what's going to happen is that we don't do that. So this is a pre-parsing process. So we'll do the tagging, but in those situations where the tag doesn't really have enough information to make its decision, because in this top example we won't, in the tagging stage, try and combine categories together. We don't know where it attaches. If the tagger isn't really sure, it will assign more than one category potentially, and then let the parser decide. So this idea of almost parsing is that we'll only do the parsing at the tagging stage if we're absolutely certain we've got it right, or well, absolutely certain, according to our probability model. And that still gives us a speed up, because it turns out that we can make a lot of these decisions using this simple tagging process and make the right decision, or at least reduce the number of categories that the parser has to consider. So just to give you one example, I've not got it on the slides, but the word is has got something like 45 possible categories in the CCG bank. Sounds a lot, doesn't it? 45. And I had an example in one of my papers. I can't remember what it is, but let's see. I don't know. He is angry, something like that. That would be pretty easy to tag. I reckon the tagger would get the correct category for is, and it would assign one category because it's looking to the right for angry. It knows what the correct category should be. So think about the speed up we've gained there. We're just passing one category through to the parser instead of 45. That's where the improvement comes from. But even if the tagger passed through 5 categories, it wasn't really sure, it's still a big improvement over 45. So I said we've got these 400 category types that we use in the parser. So how hard is this problem? Well, quite a nice baseline for tagging is to say we'll have this really simple tagging process where for each word in the sentence we'll assign the tag that it was seen with most often in the data. Just a simple baseline. I'll say that again. So for a word like road, we'd go and look in our data and we'd see what's the most common tag we ever saw with road. Probably N, and we'll assign N. And then for a word you haven't seen, you just assign the most frequent category overall. So if you do that for Penn tree bank POS tagging, you get about 90% actually. It's quite surprising, even that really simple method. Shows you how easy POS tagging is. If you do it for super tagging, you only get about 72. So I'm just reinforcing this point that this is super tagging, it's much harder than part of speech tagging. This was just meant to be a real example. This is a sentence in the tree bank, actually not all of it, it's about 45 words long. So these are the categories that we're trying to assign. And just to make the point that, remember, when we get to the super tagging stage, we've already done the part of speech tagging, because these are going to turn out to be really useful features for the super tagging. So we already know that, it's not a good example, that review is a common noun, because the pos tag has told us that. So given the words and the pos tags, the super tagging task is to assign the categories to each word. So of course we can apply the maximum entropy tagger in the standard way. I should have said that if you do that for part of speech tagging on the pen tree bank, the per word accuracy for a standard test section is about 97.2, which is about as good as you can get at pen tree bank pos tagging. So that's pretty good. I mean, it's almost a solved problem, I would say, that sort of part of speech tagging. So that remainder that you're left with is probably due to inconsistencies in the tree bank or annotators not agreeing or something like that. Now, super tag is much harder. And in fact, it turns out that if all you do is assign a single lexical category to each word, the per word tagging accuracy is about 92. Now that might sound okay to you, but just have a think about how many errors on average per sentence the tagger is going to make at that level. This is per word tagging accuracy. So if your average sentence is around 20 or 25 words long, which it is in newspaper data, you're probably getting around 2 errors per sentence. So that's no good. So per word tagging actually has got to be a lot higher than that. And I'm not going to go into details with this, but we have quite a simple way of dealing with it. It turns out to be very effective. What we do is, for each word in the sentence, remember we have a probability distribution over all the possible categories. So for each possible category for the word, we know a probability. So we have a simple way that allows us to assign more than one category. What we do is we take the probability of the highest scoring category, so say that probability is 0.8, and then we have this factor beta, so let's set that to say 0.1, and what we'll do is we'll assign all categories whose probability is greater than 0.1 times 0.8. So let me say that again. So imagine we're trying to assign a category to some word. We've got all the possible categories here, and we've got a distribution over all of them. So we know the probability of the top one, the second one, the third one, and so on. Let's suppose the probability of the top one is 0.8. We've assigned beta to be 0.1. It just basically gives us a window, and we'll say, OK, within that window, we'll assign all of those. And what's nice about this method is that if there's one clear winner right at the top, so there's some category that's probability of 0.99 and the rest are all very low, we'll only assign one category to it because we're pretty sure in that context that the tagger's got it right. So sometimes we'll assign just one category, other times where we're not sure we might assign 10. That's how the tagger works. And now we've got accuracy per word of around 97%, and the ambiguity is only about 1.4 categories per word on average. Very good. So we're still only assigning a small number of categories per word. Most of the time 1 or 2. And we've got very high per word accuracy, and that's going to do our job as a super tagger. Any questions at that point before I go on to chart parsing? Yeah, thanks.
So this is the accuracy for each word.
Yeah, per word.
So this means so let's say for each word you have 5 tags. If one of them matches the reference, then your content is correct.
Oh yeah, that's a good question. Yeah, so if that's a good point. If I've assigned 5 categories to a word, I award myself a point if the correct category is in that 5.
So I guess the tagging, the initial pos tagging seems a sort of arbitrary step in a way. I mean,
Yeah.
it's not giving us any additional information that we couldn't just feed directly into super tagger. So have
Yes.
people done experiments on sort of different levels of granularity at that level? Sort of if our pos tagging is getting simpler or more complicated before we pass things on to super tagger?
Yeah, that's a good point. Because of course, so what happens at the super tagging stage is that the features become very simple. They're just the words and the pos tags in the 5-word window. So we don't use things like the last 3 letters of the word. And the reason we don't do that is because they've already been used at the pos tagging stage. So for that example we had where there was an ED, maybe I can get an example here. Well, I guess review. So even something like review, you see, I mean, this is ambiguous here. It could be a verb. So the way the pos tagger decides is it looks to the left and sees the word 19, looks to the right and sees of, almost certainly a noun and not a verb, a common noun. And then once the pos tag has made that decision, the super tag is absolutely sure it's a noun and not a verb. It's really easy. But I guess your point is that, well, all that information that's in the pos tagger could, of course, go straight to the super tagger. Yeah, I don't know if we've... I guess I must have tried that. I mean, let me say a slightly different point, which is that if you ignore the pos tag features for the super tagger, I think you lose about 2%. But I can't remember if that's including all the features that the pos tagger would have. So, okay, so I don't know if I answered the question, but just to summarize, I think the basic point is that you're right, the pos tagging stage from a CCG point of view is somewhat arbitrary, and it's really a practical device for better super tagging. Does that answer the question? And maybe you had another point as well. Yeah.
So could you talk a bit about how the parsing accuracy would vary as the super tagging accuracy varies? So if you had 100%
Oh, yes,
super
yes.
tagging accuracy versus 90%.
Yeah, that's a great question. So I know what happens if you assign a single category to each word, which is that very often you can't get an analysis at all. So it's really a coverage problem. By coverage, I just mean, can we get some analysis for the sentence? Off the top of my head, you must lose 30% coverage, something like that. It's really quite high. Because the point is, if you haven't got the correct category, because these things are so detailed, you've really got no chance of getting an analysis. Now, in terms of the accuracy of the parse, I mean, what if... and we sort of played around with quite a few of these parameters. It sort of turns into a game where you tweak the super tagging parameters a little bit and change the accuracy and see what happens to the accuracy of the parser. But I think the basic point is that you lose out a lot of coverage if you go all the way down to 92. I don't think I could say a lot more than that. Is that okay? Yeah. So it just turns into one of those games where when you're building one of these things, I spent months doing it, you just play around with a lot of these parameters, you test on your development set and see what happens and so on. And I think the setup that you'll be playing with this afternoon has been optimized to quite a fair extent over years of playing around with those sorts of things. Okay, so let me go on to the chart parsing part. Again, I'm not going to go into huge details about this. I think I'll probably end up saying a bit more about the perceptron, but let me just tell you a little bit about how the parser works in terms of the algorithm. So a chart here is just a very simple tabular data structure which tells us for each spanning sequence in the sentence what the possible constituents are. So I think I've got a picture here. It's easiest to see. I've gone back to context-free grammar notation, as you'll see, but it works in exactly the same way for CCG in terms of the algorithm. So the way you read this chart is you can see you've got the words here along the bottom. It's the saw a man with a telescope example. And the numbers up the vertical axis are the length of the span. So let's just look at an example. So if I take this, these are called cells, these squares. If I take this square here, or this cell, you can see we're starting out at word 2, the word saw, and we've got a span of 3. So in that cell, we'll store all constituents for the subsequence saw a man. So in this tabular data structure, we've basically got every possible subsequence of that sentence represented. So the way the algorithm works, CKY algorithm, is basically we just fill this tabular data structure in bottom up. So we increase the size of the span. So first of all, we'll do the tagging stage, which for this context-free grammar example is just doing part of speech tagging, but for CCG it would be the lexical category super tagging. So for each word, we assign one or more possible tags. So we fill in that bottom row, and then we go to the next row. So for example, we'll look at this cell here, which starts out at word A, has span 2. So we're looking at the subsequence a man. We would apply all the possible rules at that stage that could possibly combine categories together that were in this cell for A and this cell for man. So in the CCG's case, we take all the lexical categories in these two cells and combine them together in all possible ways using the rules, including type raising and so on. And then all those possibilities would go into this cell here, span 2. And then again we move up to span 3 and so on. So you can see that, well, this looks like it ought to be cubic actually, because you've got one n across here, one up the top, and then there's another n factor which is all possible combinations of the various cells. So let me tell you what I mean by that. So there's one variation I've not talked about, which is if we think about this cell here of span 3 starting at saw, so saw a man, there are two ways that we could consider building constituents. We can take all the constituents for saw and all the constituents for a man, or we can take all the constituents for saw A and all the constituents for man. So we're just considering all ways of breaking up that subsequence of 3 words. So for a context-free grammar, CKY is complexity cubic in the length of the sentence. And in fact, I think I just put the pseudocode here. I don't intend to go through this in detail, but just to show you how simple it is, really. That was the point. So we loop over the span, which is going up the vertical axis of that chart, then over the start position, which is just moving across a row, and then all possible ways that we can consider of putting a constituent into the cell. So let me just back up a little bit. Yeah, so that's the basic idea. We're just going to go bottom up and in that chart and consider all possible ways that we could build constituents for every possible subsequence. So like I said, there's no sort of clever deciding to do type raising here and there. We just do everything. Yeah.
So you didn't talk about randomization at all, but then being all the rules already randomized?
Oh, binarization. Yeah, so CKY requires a binarized grammar. That's a good point. Now, it's we're already at that position with CCG because the grammar rules are already binary. Because you only ever take at most 2 categories and combine them together. So we don't need to worry about binarization. That's a good question. All right, so the other thing I wanted to talk about here is this question we had in the first session, which was how can we possibly store all these analyses? So I talked about millions, possibly more possible derivations for a normal sentence of newspaper text. So the basic idea here is that we're going to use something called a pack chart. I mean, a chart sort of naturally packs. I think the very idea of packing is sort of at the heart of this sort of tabular data structure. So let me show what I mean with this example. So in this saw a man with a telescope example, remember we've got this ambiguity where we don't know whether the seeing was being done with a telescope or the man was being done with a telescope. And I've tried to represent that up here. So we're right up at this cell, starting at the word saw with span length 6. So we've got the subsequence, saw a man with a telescope. And there are 2 possible verb phrases there, which I've represented with 2 VPs. So one of them, well, I'll let you look at the details, but basically those 2 VPs represent the 2 different analyses. So the idea is we've already built up those 2 possible analyses all the way up here, and we've got these 2 VPs. Now, the idea of packing is really simple. All we're going to do is that we'll just put those 2 VPs together into a single equivalence class. So they're completely equivalent because they're the same non-terminal spanning the same subsequence in the sentence. And what that means is then for any future parsing, in this case combining this VP with this pronoun to give a sentence, we'll only use the one VP. That's the key idea. Now, of course, packing will happen all the way down in the chart as well. Just that in this nice example we've got packing, it's easy to see right at the top. And what we achieve with that packing is that we can represent an exponential number of possible analyses in this polynomial space. So we don't get this blowout. But all the derivations are there. But they're in this very efficient so-called pack representation. So the last question is, we've got this, so on to step 3 now. We've built up this pack chart. All the derivations are there. We want to find the one highest scoring one, because we'd like the parser just to print out one derivation or one analysis. How do we do it? It's a little difficult for me to talk about this at this stage because I haven't yet told you about the parsing model. But let me just give you an intuition. It's very simple. All the Viterbi algorithm does, and this is the same intuition that you had for the tagging problem with Viterbi, is that when we look at these 2 VPs here, in order to find the highest scoring derivation, we only need to consider the highest scoring VP. Because there is no way that let's suppose the highest scoring VP is the one on the right. That's got some score attached to it that I'm going to explain in the next section about how we attach scores to constituents. But let's suppose the highest scoring one is on the right. There is no way that the one on the left can be part of the highest scoring derivation. That's the basic idea behind the Viterbi algorithm. Now, I've gone over that very quickly, Probably a little bit too quickly, but I wanted to move on to the perceptron and spend a bit more time on that. But can I answer any questions about the chart parser at this stage? So I guess the ideas are fairly simple. We've got this nice tabular data structure. We fill it bottom up, so we've got all constituents for all subsequences covered. And whenever we've got two labels of the same type spanning the same subsequence, we put them together into an equivalence class. And we just pick the highest scoring one when we want to find the highest scoring derivation. Okay, so let's get on to the parsing model. So this is the thing that will assign a score to a derivation. And again, it's a feature-based model. So it's similar to the maximum entropy model that we saw for the tagger, but this time it's just a linear model. So it's incredibly trivial form in terms of the scoring function. So I want some function here which takes a derivation d and a sentence s and assigns a score to it. This is the thing we're going to use to select what we think is the best derivation. And you can see it's got this really simple form. We're just going to take features again, and these are functions of the derivation, each one with an associated weight, and just add up the product of each feature together with its weight. So in fact, we can write it as this dot product. If you imagine that all the weights are in some vector lambda bar, and all the feature values are in some vector, it's just a dot product of the two. Now, what's slightly different about this model compared to the tagger is that in this model, the features are integer valued. So before we had those binary valued features that just sort of picked out elements of the context, if you remember. In this case, it's just a slight generalization of that. Rather than saying whether some particular feature is present in a parse or not, we'll actually count them. So let me try and give you an idea of why we might want to do that. So let's think about what sorts of features might we want to apply to this derivation to tell us whether it's a good one or not. Well, one feature that's going to be really useful, one feature type, is all these rule combinations. So we'll have one feature that basically counts the number of times in a derivation that we see an MP combined with this S back MP to give an S. That will be one feature. And the reason we want to count it is because we might see that rule derivation more than once, that's all. But again, it's the same intuition that we're trying to pick out elements of this derivation that tell us whether it's a good derivation or not. So basically we'll have a feature that covers every possible category combination we've seen in the tree bank, in our data. What else will we have? We're going to have features that tell us the lexical category that's been assigned to a particular word. So we'll have a feature that picks out this bit of the derivation. And again, in theory, integer valued, but here it's really 1 or 0. So a feature that says this word 2 has been assigned this particular category in this derivation. We might also print out some this sort of dependency information. So you can imagine a feature that says, in this particular derivation, the subject of the verb persuades is Marx. But the basic idea is that these features are going to be mainly local to these rule combinations. So whenever we combine two categories together, or we have a category assigned to a word, that will be a feature in our model. So as I said, mathematically, down at the bottom there, each feature is a function from the derivation space onto the natural numbers. So given a derivation, it just counts the number of times you see some feature configuration. And I just wanted to put this on here to indicate how many features we might have. Again, because features are based on words a lot of the time, it can be a huge number. And in the last model, we were using around 3 million features. So it's quite a significant machine learning problem. We've got 40,000 sentences of training data, and we've got to learn a weight for 3,000 different features. That's our machine learning problem. No, 3 million, I'm sorry. 3 million features. So it's really quite a lot. Oh, I've got that the wrong way around, yeah, thanks. I made that mistake a lot. Is there no one else have that? I think it's maybe because you want to write that for... No, I don't know. I don't know what it is. Yeah, it's the other way around. Okay, so I've talked about the linear parsing model. One question... Obvious question is, where do the features come from? Well, you sort of define those by hand, use linguistic intuition, is how it's often described. And we don't do any sort of automatic feature selection or anything like that. So we effectively define feature types. So we say, well, I reckon a really good feature will be one that looks at what category combinations there are in the derivation, an obvious one. That's a feature type. And then that's instantiated by all the possible feature combinations. So you sort of play this game of trying to think of what features might be good. You add them to the model, you test the model on some data using evaluation metric I'll come on to later. And typically after you've done quite a lot of work, you discover it doesn't make much difference. So I don't know if you've had enough experience of playing with language processing yet to realise that this is a really hard problem. And of course when you start out, you naively think, as I did as a PhD student, that I've got this really great idea, it's going to make a difference. You soon learn to become a bit more sceptical than that. And certainly in my experience, a lot of the stuff that you try when you're playing around with these models doesn't often help. I mean, the story about language processing is this. It's really easy to get to a point where the performance is okay. Really easy to build a pos tagger that does 93%, 95%. Getting a little bit better than that is really hard. And that seems to be true across all language processing tasks. So it's the same with machine translation. You can build a basic SMT system that does okay, probably looks fairly impressive if you think how hard the MT system is, and then you spend the next 10 years trying to improve the blue metric by 2 points or whatever it is. It's the same with parsing. Okay, so fine, let me get on to the perceptron. So this is a really interesting training algorithm. So it was introduced by Michael Collins to the NLP community. Of course, the perceptron's been around for years, since the 60s. But this is how we can use it to solve these, what are often called structural prediction problems. Structural prediction because we're given a sentence and we're trying to assign a whole structure to it. So it's a structured machine learning problem. Now I've given you the algorithm here just to show you how simple it is. I'll walk you through an example and you'll see exactly how this thing works. But remember the problem is that we've defined all these features by hand, of which we've got about 3 million. We've got 40,000 training sentences where we know the correct derivation. And the learning problem is basically assigning values to those weights. So how are we going to do it? I think I'll just walk you through the example. So we start out with weight values of all zeros. So here are my weight values right at the top. We've got 3 million of these things, all 0. And we take the first sentence in our data, sentence 1 in the tree bank. And we parse it, build up our pack representation, as I just described. And then using the weight values that we've got, we find the highest scoring derivation using Viterbi. This is often called decoding. Now, let's think about what happens at this point in terms of the features that we get back from that highest scoring derivation. Some of them, which I've got here in blue, will be correct. Also, the blue here is meant to be the categories that I actually put together to get the derivation. I'm not sure those categories actually work, but you get the basic idea. I've done some decoding. I've got a single derivation. So I read the features off that single derivation. Some of them will be correct in the sense that the features on that derivation will also be on the correct derivation in the tree bank. So remember, we know what the answer is. That's in our training data. Some of them will be incorrect. So these are the ones in red. These are the ones that appeared on the highest scoring derivation, but don't appear in the correct tree bank derivation. So they're wrong. And then the ones in green are the ones that should have appeared on the correct derivation but didn't. So they're on the correct tree bank derivation but not in our output. So what's an obvious way to update these weights? Because what the way to think about the perceptron is that it's basically, what it does is it forces the parser to parse the training data correct. And the way that we do that is a really simple update. So you can see that for the idea is that the features in blue, the ones we got correct, we won't bother updating those at all because we're already getting them right. So let's just leave their weight values as they are. The ones in red we got wrong, we'll take one off their weight value. So we're trying to say to the model, look, this is probably a bad feature. It shouldn't have appeared. So let's downgrade that weight. And the ones that we should have got coming out that we didn't, the green ones, we'll add one. Because we're trying to force the parser to produce those features. And the way to do that is to give them high weights. Because that means next time we look at this example, there's more chance of getting a derivation that's got those green features on them. So one thing to notice straight away is that this process is called an online process because we update after every single training example. As opposed to a batch process where we take the whole training data, all 40,000, and do a single update looking at all 40,000 at the same time, if you like, and then sort of do some iterative process. Here we're updating after every single training example. So we've done the first sentence. Let's go to the second one. We do exactly the same thing, but now we take the weights that we got from the previous example. So using those weights, second training example, build the pack chart, find the highest scoring derivation, decoding. Again, we've got the same story. Some features that come out will be correct, we'll leave those alone, they're fine. The ones that come out incorrect, we'll take one off. The ones that should have been there that weren't, we'll add one. And that's it for the perceptron. Incredibly simple. And yet, surprisingly, it works really well. So it's been used to build a state-of-the-art pos tagger. It does really well on the parser. Yeah.
So when you generate the pack forest, do you actually do coding?
No, that's a good question. So one of the things we'll be looking at in the workshop, actually, one of our tasks, is to see whether we can improve the efficiency by doing some pruning at the parse stage, the chart stage. At the moment, given a particular set of lexical categories, we build everything. There's no pruning at all.
So how big the pack forest is?
Oh, that's a good question. You mean in terms of memory footprint? Or?
Like how many categories you have in the pack?
Oh, well, we could have millions, billions of derivations. I'm not sure that number of edges. I don't know. How many edges does that correspond to? That's a good question. I could find that out for you. I don't know off the top of my head. In terms of the memory footprint, one of the nice things about this process is that you only have to read in one of these things at a time. If you imagine a batch process where we're updating using the whole training data, you'd have to have these in memory for all 40,000. And we've done that for a separate kind of training, but we had to do some sort of parallelization, splitting it up across machines. But here, each one of these things only takes up about 30 megabytes. So we read it in, do the update, throw it out, parse the next sentence, read it in, do the update, throw it out. It's online.
So the perceptual algorithm will require you run through the data for many times, right?
Yes,
You
yes.
actually store the forest on the disk, or you actually go every time?
Oh, that's a good question, yeah. So what's happening in practice is, first of all, the perceptron updates on every sentence, but we'll run through the whole data maybe 5 or 10 times. So we're updating on each one, but then we pass through again. And you just keep going until, well, I guess the way you do it in practice is you try some number of iterations and see what effect that had on the development data in terms of accuracy. Now, the way that it works in terms of our implementation is that we've got a nice way of storing these packed forests on disk. So we parse once, store all of these on disk, and then we just read them in to do the decoding. So we don't actually parse every time. We do the parsing once, store them on disk, and just keep reading them in. And we can do this training in about 3 hours, which is really good for the size of this sort of model. Yeah, okay. So, so just related to this point, the perceptron training sounds incredibly simple and trivial, and you might think, well, you know, what is there to say about it? But there is something to say about the practice of using the perceptron, which is that actually it's quite expensive, because every single training sentence we have to do this line here, which is basically just calculating the derivation that maximizes our score function, so the highest scoring derivation. So another way of saying that, we have to parse every sentence of the training data, say 10 times if we're doing 10 iterations. So we might have to parse effectively 500,000 sentences. Now, you can only do that if you've got a relatively fast parser. And we have, because of that super tagging stage that I've been talking about. So one of the nice things about the parser is that not only is it fast so we can potentially parse lots of data, we can also do this sort of perceptron online training very fast as well. And that's this slide here. So this I've already talked about the almost parsing. Oh, and I mentioned this point about the very small memory footprint, 20 megabytes I've got on there. Okay, 5 hours for 10 iterations. So I think at this point I was actually, I was going to give you a quick demo of the speed. See if I can do that. So what I'm doing here is I'm parsing what's called section 23 from the tree bank, which is a standard test set that's used for evaluating these parsers. And basically what's happening is I'm printing the output to a file, but this log file is telling you the number of sentences that we've parsed, just flashing down the left-hand side. So this is sentences of newspaper text. I'll perhaps show you some examples of kind of sentences we're doing in a moment. So you can see it's pretty quick. I mean, I don't know what your expectations are about how fast you might be able to do this sort of parsing, but this is sort of orders of magnitude faster than we could do sort of 5 or 10 years ago. Well, 10 years ago that this would have been unheard of, I think. Now, of course, computers have got faster and so on. That's a factor. But also the fact that we're using this super tagger, and we've got some highly engineered C++, I should make that point as well, is what allows us to do parsing as fast as this. So I'll just let it go. It's almost finished. I've got some coverage numbers on there as well. So the coverage is the percentage of sentences for which we receive some analysis. Not necessarily correct, but some analysis. So that's, where's that? Here. So 99.5%. So there are some sentences, that's about 7, I think, out of 2,400 odd, where we just couldn't get an analysis and we effectively gave up. But you can see it's really quite robust. We can get an analysis for almost everything. How fast were we going? For this particular version I've got on here, just running on my Mac laptop, 40 sentences per second. So one thing, a big part of our project, large-scale syntactic processing, is trying to get those sorts of speeds or higher for web data. So we'd really like to get to 100. I suspect that might be a bit too much for us. Because the thing about the web data is that we won't have models, the models are tuned for newspaper data. So it automatically makes it a bit slower on web data because suddenly things look a bit different and maybe a bit more ambiguous. So my guess is that 100 might be a bit ambitious, but that's what we're aiming for. Let me just show you the kind of sentences that we're talking about. So that's just some newspaper data. So my point is, it's real stuff. It's not sort of made up. It's the kind of thing that you get in naturally occurring text. And I think on average these are about 25 words long in this particular corpus. Okay. So I think the last thing I wanted to talk about was evaluation. So an obvious question is that I'm sure I'll get asked this a lot on Monday when I'm giving the opening talk when we start the workshop, which is, well, how accurate is this thing? First of all, there's an issue of how you evaluate parser accuracy at all. Turns out to be quite a difficult question. But of course, one thing we want to do is take the output of the parser on some example sentences and compare it with what's often called a gold standard. So this is some output that we think is correct or we know is correct because it's been produced by a human annotator. And there are various metrics that you might use. So one would be an exact match, namely you get a point if you get the whole sentence, the whole derivation correct, or 0 otherwise. And people do use that. That's a little crude because, of course, it doesn't tell you if you got a 0 whether you were close to getting the derivation correct or whether it was completely hopeless. So people normally use some sort of partial match. And I think the best method available at the moment, in my opinion, is evaluating against a set of so-called grammatical relations. So let me show you. It's quite intuitive. So the idea is that we have a gold standard set of these sorts of relations that a human annotator has created, a linguist. So you can see it's that sort of dependency relation. So in this example, we're just representing the fact that in this sentence, she is the subject or the non-clausal subject. That's what the NC means of gave. There's some indirect object relation between gave and to, determinant relation between the and present, and so on. Now, obvious question is, well, where do you get that ontology of relations from? This was created by Ted Briscoe and John Carroll, some people in the UK. Contains around 10 different relations, I think. I mean, we could sort of argue about what the correct set should be, and people do. But this seems like a reasonable set to use. Just a few more. Well, this example is meant to show that sometimes we have relations between more than 2 words, so this ternary relation, some sort of clausal complement relation. The details aren't particularly important. But you get the basic idea that we've got this fairly theory-neutral representation of the meaning of the sentence, and that's what we want to evaluate against. Now, one problem straight away is that the CCG parser doesn't know about these grammatical relations. So everything you've seen so far in the tree bank and so on, there's no nominal subject or direct object or anything like that. So the first thing we have to do is make the CCG parser produce these things. I don't want to go into the details too much here, except to say that the way we can do it is first we have what are called what I call CCG dependencies. So the idea here is quite simple. All I've done is I've taken those argument slots in the lexical categories and basically numbered them. So basically there's going to be some relation here which consists of the lexical category. This is for the transitive verb. So we'll direct object and subject. And I've just numbered the subject relation with a 1. So that pair represents the subject relation for a transitive verb. Likewise, when I put a 2 there, it's the direct object relation. And what I've done, I did this manually myself. It took a long time and it turned out to be quite difficult. But I created a mapping that said, whenever I see this sort of relation coming out in the parser output, I'll call that a nominal subject. And I'll fill it with these words. That just means the word associated with the lexical category. And that's the filler, the head word of the noun. So if I've got something like John eats potatoes, then that would be represented with this category associated with eats, and we'd have eats here and John as the subject. So my basic point here, I'm not too concerned about the details, is that we have a way of taking the CCG output in terms of lexical categories and producing these sorts of so-called grammatical relations. So we can evaluate. So you must have seen these sorts of metrics now over the last 2 weeks, precision and recall, completely standard set of metrics. So the precision basically says, out of all those relations proposed by the parser, how many do we get correct? And the recall says, out of all those relations that are in the gold standard created by the human annotator, how many of those do we get correct in the output? And you can combine them together using, this is a standard way of doing it, to get a single number, so-called F-score. And this is what happens. So I should tell you a little bit about the data. This is on a data set of 700 sentences, again from the Wall Street Journal, taken from the Penn Tree Bank, annotated with those sorts of relations I've just shown you. And these are the precision and recall numbers you get, and an F-score of about 83. And I think this is about the best score I've seen on this particular test set. So let me just say one thing here. You may have seen parsing results up at about 92, something like the Charniak parser, but that's using a different sort of evaluation metric, so-called parseval, which basically doesn't use these grammatical relations. It looks at the phrase structure trees in the Penn Tree Bank and tries to compare them. And there are various papers in the literature which argue that actually the parseval metrics are probably a bit too easy in some sense. I mean, it's quite an interesting question. You know, if you show this number to someone and say, parsers are 83% correct, what does that mean in isolation? What is that 83 number? But I always say at this point that if it means anything to say there is some number which represents how good parsers are, I reckon 80% is about right at the moment. I'd say 90 is too high. Yeah.
So, two questions. One is like how much the perception training actually helps you?
How much does the perceptron training help? Or what do you mean? I mean, compared to...
This sort of like perception training, isn't it?
Yeah, so this has got... Yeah.
What if you just do the regular maximum accuracy estimation of the timing?
Oh, I see. So if you wanted to use some other sort of model. Well, we've done other kinds of models. So we've used a maximum entropy or a conditional random field style model, which you might have heard of. That the perceptron does as well, which is surprisingly. So the perceptron's the best sort of model I've found for this particular parser. If you wanted to do a standard sort of generative model with a maximum likelihood estimation, Julia Hockenmeier did one of those and didn't perform as well as this, but it's not quite clear the two are exactly comparable. It's a little tricky, you see, because you'd have to produce a generative model that had exactly the same feature set, and you'd have to make sure that you worked really hard on the smoothing and so on. But so the short answer to your question is I think the perceptron performs about as well as anything on this task that I know of. I mean, whether you could get a support vector machine or something like this, that to work on this, I really don't know. But I think the perceptron does very well. Now, one of the nice things about this evaluation is that I've just given that 83 number. As I said, what does it mean? You can break them down, the numbers down into particular types. So, for example, I know that the parser is really good at direct objects of verbs and prepositions, almost 90%. Does okay at subjects, about 80. Not so good at coordination, which is conj, down at 77. So you can see that some of these numbers are actually quite a bit lower than certainly the 90% you sometimes see in parser evaluations. And the other thing to say is that, of course, in that 83 number I've just given you, there were some really easy relations, so things like determiner relations. Not surprising, we're up at about 95. But these aren't very interesting. I mean, who cares whether the parser knows that the word the attaches to some noun? Likewise with auxiliaries, not so interesting. Okay, so I've almost finished. Just a few slides right at the end. I've not got an awful lot to say about this, but of course I'll be talking a lot more about this on Monday when I introduce our team. But we're interested in parsing the web. So an obvious question is why do we want to do this? Well, I've already talked about the semantic search and question answering motivation. Another motivation we've got is that we'd like to provide massive amounts of data for knowledge acquisition. So learning the linguistic properties of words, trying to gain world knowledge from web data, that sort of thing. We think that parse data is very useful for that. And the basic problem we've got is that, of course, we need a fast parser if we're going to process, well, billions of web pages. You know, even with the number of machines that Google has available, we really need a fast parser. And there's also this issue that I haven't really talked about very much, which is that we've got this parser trained on newspaper text. How well is it going to do on web data? Wikipedia data, I should say. I mean, of course, web data is full of lots of different domains. We're going to be focusing on Wikipedia. So that's one of the questions we'll be investigating. Oh, that was where the speed down was supposed to come in, so I've already showed you that. Just to give you some idea of what the sort of thing we can do, previously we've used it to analyse 1 billion words of text using just 18 computers in less than 5 days, which is really pretty good. I mean, you just couldn't do that 5 or 10 years ago. So just to conclude, I think the basic story is that I hope to have demonstrated, in fact you'll get a chance to play with the tools this afternoon, that we can now do robust and what I'm calling linguistically motivated parsing of real text. Just to come back to this point of whether it can really help in NLP applications. So I'll just tell you a little anecdote. When I came to Hopkins in November to try and pitch to get this project up and running, and we were talking about, well, what are parsers useful for? Someone in the audience, I won't say who, I thought asked a really good question, which was, what are pos taggers good for? Who uses part of speech taggers? And it's kind of an interesting question. You know, if you think about something like Google, how much language technology do they really use, or could they ever use? Now, you might argue that eventually this sort of parsing technology will be useful. We just haven't got it to a stage yet where it's good enough. And I believe that. And we should keep working on parsing anyway because it's an interesting problem. But still, it's actually quite a tough question to answer. You know, why should someone spend all this money on parsing technology? What's it really good for? So what's left to do? Well, you see that there's still quite a lot of room left for accuracy improvements. So if you read the parsing literature and look at different sorts of evaluation metrics, the ones that I've shown you, you might come away thinking that parsing is almost a solved problem. You know, just a few more years tinkering, a bit of incremental improvement, and we'll be up at 90% accuracy. I think absolutely not. Parsing is still a really hard problem. And in fact, I think one way I like to think of it, it's not clear to me that the statistical revolution for parsing, there's a sense in which all it's really done is allow us to solve the easy problems, I think. So those sorts of long-range dependencies that I showed you earlier on in the talk, I've recently done an evaluation seeing how good parsers are at recovering those sorts of things. They get about 50%. I mean, that's still really hard. And statistical methods haven't really helped us very much in solving that problem, I don't think. And the obvious problem is that we've only got this 1 million words of training data. So a really big issue that everyone's thinking about in language processing is, can we find cheap ways? We can't spend years doing this annotation all the time. Can we find cheap ways to get more training data to try and improve parsers and other kinds of language technology? Okay, I'll stop there. So have fun in the lab this afternoon. I'll take some more questions. Yeah.
So I still want to get a sense of how accurate between this CFP, CCP parser and this CFP parser, right?
Oh, okay, yes.
Is there any way to, I mean, you just made the increase in that?
Yeah. This is a really nice question. So the question is, everyone maybe knows about the Charniac and the Collins parser, and something that people always ask me, it's a good question, is how does it compare to Charniac? So with James Curran, I recently did some work, and we've got a paper in ACL this year in the short paper session, where we compared the output of the Berkeley parser, this is well-known parser from Dan Klein, with the output of the CCG parser. Now, how do you do it? Well, you think the obvious thing is you take the output of the CCG parser and you convert back to the Penn tree bank. Because, of course, the CCG bank came from the Penn tree bank, right? Now, that conversion is really hard to do. Because, as I said, it wasn't just a case of deterministically relabeling nodes in the Penn tree bank tree. There had to be some moving around as well. So what we did, we took sort of a fairly old-fashioned approach. We wrote lots of rules manually that takes a CCG tree and turns it back into a Penn tree bank tree. And what we found was that we could do this process perfectly with no loss in this conversion step for about 40% of the Penn Treebank sentences. So we've got this subset of the standard test set, which we know we can do a fair comparison with the Berkeley parser. And we got statistically similar results. They were indistinguishable. So on that 40%, of which the average word length was about 18, so it wasn't as if they were dead short or anything like that, we were at the same level as the Berkeley parser. So I think we're doing as well as these Penn Treebank parsers. And of course the other thing to say is that this parser wasn't designed to create Penn Treebank trees. It's not optimized for that. In a sense, it's not very interesting. I don't want to produce Penn Treebank trees. And we just did it for the evaluation. So another question would be, how well does the Penn Treebank parsers like Collins and Charniak do on this sort of grammatical relations evaluation? And people have tried that. So they've taken the output of the Collins parser, wrote rules to produce those grammatical relations, subject, direct, object, and so on. But then, and then the Collins parser doesn't do very well. But then the complaint is always that, yeah, but your mapping isn't good enough. And it's true. I mean, there is always a loss in this sort of conversion process. So the whole issue of parser evaluations turns out to be quite an interesting one. Any more questions? Yeah.
So the task that you just said parsers are only getting 50% on.
Yes.
The attachment or conjunctions or what?
Oh yeah, okay, that's a good question. So let me say a little bit more about that. So no, I mean these sorts of sentences I had right at the beginning. So yeah, so let me tell you exactly what we did. So this is a paper that's coming out this year as well. Oh no, I've gone too far. That one. So what we did was we took 7 types of grammatical constructions that license these sorts of unbounded dependencies. So extraction out of relative clause is one of them. So for this particular construction, we took 100 sentences from the Penn Treebank and we manually created some data which basically says in the gold standard the direct object of bought is company. That's the only thing we have in the gold standard. And we just want to measure how many of those dependencies does the parser get. And we took the CCG parser, another parser developed at Tokyo based on a different grammar formalism but using very similar techniques, and 1 or 2 other parsers. And for that particular construction, I think the accuracy was about 59%. We also did some right node raising, like that one. So we found 100 examples of right node raising sentences, and for that the accuracy was about 50. For the CCG parser, it was worse than that for lots of the other parsers. And we had 5 other constructions as well. Now, we also measured how frequent these things are. So something like that in newspaper text turns up in about 1 or 2% of sentences. So it's not very frequent. And that's why I said that if you're in the business of improving that 83% number that I told you about, you wouldn't bother with these because they're not going to do anything for you. And that's why we've created this new test set, because we're hoping that people will start playing this evaluation game instead. Yeah, thanks. Okay, let's stop there. I'll see you this afternoon for the lab. Thanks.